Welcome. The topic we are going to discuss in this lecture is some graph operations. Okay. So we'll be discussing this under these three headings: traversal, connected components, and spanning trees. So in today's session we'll concentrate on traversal. Okay. Like how we have discussed about tree traversal techniques. Basically we have discussed three tree traversal techniques: pre-order traversal, in-order traversal, post-order traversal. And also we have discussed one more traversal, level order traversal. The implementation of that we have not discussed. Okay. Other three techniques we have also implemented. So similarly, there are two commonly used graph traversal techniques. One is called as depth first search, which is in short called as DFS, and the other one is called as breadth first search, which is in short called as BFS. Okay. So depth first search, it is equivalent to a pre-order tree traversal. Okay, but we have discussed pre-order traversal for a binary tree. But when you take a graph, there is no, I mean, each node can have any number of children. Okay, but its way of working is similar to that of a pre-order traversal. And when you see breadth first search, its way of working is similar to level order traversal. Okay. So first let us discuss on depth first search with a example graph and let us see how it works. So consider this particular graph. If you apply depth first search on it, then what should you do? Start with the root node. Start with the root node. First visit the root node. Visit in the sense here we just display that. So V0 is visited. Okay. Then go to its left. Check whether it is visited or not. So far it is not visited, so visit it. Okay, then go to its left. Is this visited or not? No, it's not visited, so visit it. Then go to its left. There is no left. Is there any other pointer? I mean, we visit all the child of a particular node. Okay, we visit, but we visit depth wise. We visit depth wise. I mean, one branch first we complete, then we do the next branch like that. Okay, so that it is called as depth first. Okay, so coming to this node, there is no left child, but it has some other pointer to a node V7. So V7 is visited or not visited, so visit it. Now V7, from V7 you see what are the things are there. From V7, V3 is already visited. What about V4? Is it visited or not? V7 we have visited. From V7 now we are checking. V7 to V3 is visited. V4 is it visited or not? Visit it. So visit V4. Now you are in V4. From V4 what are there? V1 is there which is visited. V7 is there which is visited. You reached V4 from where? From V7. So go back to V7. As as all the nodes from V4 were visited, you have to get back to V7. Okay. From V7 again if you see V3, V4 are visited, what is V5 is not visited. So visit V5. Visit V5. Now from V5, V7 is visited, so visit V2. V2 is not visited. After visiting V5, visit V2. Okay, now from V2, if you see V0 is visited, but V6 is not visited. So visit V6. Okay. Now from V6 everything is visited. Right? So from V6, from where you came to V6, from V2 you came. So go back to V2. Now from V2 everything is visited. V0, V6 is visited. From where you reached V2? From V5. So go back to V5. From V5 now all the nodes were visited or all the vertices were visited. V7 and V2. From where you have reached V5? V7. So go back to V7. Okay. From V7 all the vertices are visited. V4, V5, everything were visited. Okay. From where you have reached V7? Okay, you may say either V4 or V3 because from first there are two uh, levels, right? Okay. So obviously we'll go back to V3. Okay. Again from V3 everything is visited. So go From where you reached V3, V1. From V1, everything were visited. From where you reached V1, V0, go back to V0, which is the root node. Okay, so from where you reached V0, from outside, or you can say from null. So 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 this is how it works. Are you getting? This reverse back operation is not required, but just for your understanding, I am telling. Okay, I am saying that because whenever you reach a dead end of a particular node or of a particular vertex, then you have to go back to the node from where you have reached that particular node. Okay, so this is the concept. So here, if you observe, we are visiting the nodes depth wise. First, we have visited all these nodes. Okay, after visiting all these nodes, then we checked from V7 is anything is missing or not. V4 is missing. So we visited V4. Okay, then from V4 there is nothing else. So we came back to V7. Then we visited V5. Okay, again from V5 we went to V2 because V2 is not visited. Then after visiting V2 we went to V6. We visited V6. By that time all the nodes were visited or all the vertices were visited. Okay. So this is how it works. If you take an so this is a graph. If you take a tree, let us take a tree and see how it works. Yeah, let us see in this tree. In this tree, if you apply depth first search, how it will work in the sense first visit this particular node 0, root node 0, then go to its left, go to its left. Is it visited or not? No, visit it. Okay. Then go to its left. Is it visited or not? No, visit it. Okay. Now there is no other option. Okay, so you have to from 3 only one there is a edge to, I mean from 3 there is a edge to 1. Is there any other edge? No other edge. So 1 is visited. So what you have to do? Now you have reached a dead end. So you have to return back from where you have reached 3. So you have to go back to 1. From 1 you see, is there any unvisited node? 0 is visited, 3 is visited, 4 is not visited. So go back to 4. Visit 4. Visit 4. Okay. Visit 4. Now from 4. Now 4 has reached a dead end. So from where you came to 4? From 1. Go back to 1. Okay. From 1 also now all were visited. 0, 3, 4 were visited. From where you have reached 1? 0. Go back to 0. From 0, 1 is visited. So we have to go to 2. We have to go to 2. Okay. So 2 is visited or not? No. So visit 2. Okay. Now 2 you have two options. So whenever you have more than one option, you have to go from left to right. Okay. So 2 you have two options. You can go either to 5 or 6, but we will take the leftmost option. So we will visit first 5. Okay. So we will visit first 5. So 5. Okay. Now from 5, at 5 we have reached a dead end. Because 5 there is only one path 2 and 2 is visited. So from where you have reached 5? From 2. So get back to 2. From 2 there is one thing that is pending, that is 6. Are you getting? So visit 6. Right? So this is the order in which we visit for depth first search. 1, 3, 4, 2, 5, 6. Okay. 0, 0, 1, 3, 4, 2, 5, 6. Okay. So if you see this particular graph now, this tree now, so in tree you can actually feel that depth first thing. In tree you can actually feel that how we are visiting in a, why we are calling it as a depth first search. So we are depth in the sense we take one branch, first visit all the nodes in that branch. That is always we move from the leftmost branch to the rightmost branch. First we have visited all these things 0, 1 and 3, right? Then 0 is visited, 1 is visited. So actually we are following this branch. 0 is visited, 1 is visited, so we are visiting 4. Then we are following this branch 0 to 5. 0 is visited, 2 and 5 we are visiting. Okay, then we are following this branch. Again, if you see 0, 2 is visited, so we are visiting 6. Okay, right? So this is how the concept of depth first search works. So this is actually similar to pre-order search. You can perform a pre-order search on this tree and you can verify. If you perform a pre-order search, pre-order traversal, what is pre-order traversal says root, left and right. So start with the root node. Okay, is it a root node of any subtree? Yes, so display that. Then go left. Is this the root of some subtree? Yes, so display that. Okay, then go left. This is not a root, but it is a left child. So it is a left of some other node. So after root, what you have to go? Left. Then right. Okay, so 3 and 4 will come. Are you getting? So now the left subtree is visited. From with respect to the root node is visited, its left subtree is visited. So where you have to go? Right. Is it a root of some subtree? Yes. So visit it, root. Then go to its left. Is it a root of any subtree? No. But it's a left child of 2. So 2 is visited, 5 is visit 5. That is its left child, then its right child, that is 6. Okay. So this traversal in a tree is equivalent to pre-order traversal. Okay. Depth first search in a graph is equal to pre-order traversal in a tree. Right. Okay. Now let us see how to implement this. How we are going to program this. Okay, so that is the what you call challenging part. Fine. So we are going to implement this using adjacency list. It can also be implemented using adjacency matrix, but we are going to discuss using adjacency list. So first represent this graph using adjacency list. So this is adjacency list representation of the graph. Okay, I think it's very clear. I need not explain this again. So you are creating an array of pointers. The size of the array of pointers should be equal to the number of vertices. Here we have 8 vertices 0 to 7. So the size of this array is also array of pointers is also 8 0 to 7. Okay. If you take vertex 0, it has two edges, one edge to v1, another edge to v2. So from 0 we have a node 1 and which is connected to another node 2, which means that 0 is connected to 1 and to 2, so on and so forth. It applicable for all the vertices. Okay. Now let us see how we are going to implement it programmatically. Fine. So to implement this in a program, we will maintain an array. This array we will call it as visit. This array is called as visit of a particular vertex. Okay. The array size of the visit array the array size of the visit will be equal to the number of nodes, number of vertices in the graph. So this graph contains 8 vertices. So this array size also will be 8. That is, it will range from 0 to 7. Visit of 0 to visit of 7, or vertex of 0 to vertex of 7. Okay. Initially, before starting the depth first search traversal, you have not visited any nodes. None of the nodes were visited. So initially all these entries were filled with zeros. Okay. So what this means in the sense, what this means in the sense, vertex 0 is not yet visited. If there is a 0, which means it is not yet visited. 1 is not yet visited, 2 is not yet, 3 is not yet visited, so on and so forth up to 7 is not yet visited. That is, none of the vertex is not visited. Okay, fine. Now, so I am discussing what are the data structures we are going to use to implement depth first search. The first data structure which we are going to use is adjacency list. We are going to use adjacency list. The next data structure we are going to use an array visit, which holds like whether a particular vertex is visited or not. And also we are going to use a stack. Okay, right. A stack of uh, pointers to nodes, to vertices. Okay, fine. With this knowledge, let us proceed. So first we will start with the zeroth entry of the adjacency list. The zeroth entry of the adjacency list corresponds to which vertex? It corresponds to vertex 0. Okay. So vertex 0 is nothing but what? Root vertex. Vertex 0 is nothing but root vertex. Okay. So first we will visit the root vertex. So we are starting with the zeroth entry of adjacency list, which corresponds to vertex 0. So first we will visit that. Okay. So visit in the sense first we will display that. 0 we will display. Okay. Now it is visited. The moment this particular vertex is visited, we will make in this array, it will not be no anymore 0, it will make it as 1. We will make it as 1. Okay. Then we will see what this is pointing to. It is pointing to which vertex? It is pointing to vertex 1. It is pointing to vertex 1. Is this vertex is visited or not? No. Okay, if it is not visited yet, visit it. So visit means you display it. Okay. And also make that respective entry in the visit array as 1. Okay. Make it 1. Right. Now we have visited a vertex which is not visited. Okay. Whenever you visit a vertex which is not visited yet, other than the zeroth vertex. Okay. Other than the zeroth vertex, whenever you visit any other vertex for the first time, whenever you visit any other vertex for the first time, and if it is before not visited, then you have to jump back to that particular vertex in the adjacency list. Okay, listen carefully. This is not applicable to 0 alone. Okay, root node alone it is not applicable. Whenever we visit a particular vertex or a node for the first time, we will visit it and we will make the visit in the array we will update to 1, but after that we will not continue in the same adjacency list position. We will move to the adjacency list value corresponding to this particular vertex. Okay, so now the control is going to jump from here to here. Are you getting right? But before making such jump, because previously we are in vertex 0, now from vertex 0 we are jumping to vertex 1. Okay, before making such jump, you have to push this vertex to stack. That is, from which vertex you are jumping, that vertex should be pushed into stack. From which vertex we are jumping 0, so push 0 to stack. Okay, because we have to come back here, so that we are pushing. Okay, fine. Now you jump to vertex 1. Okay, the vertex 1, so whenever you jump to a new vertex, no, always you might have visited. Always, surely you might have visited, because after visiting only we are jumping. Or you see, or could you connect it? So before jumping we visited 1, and also we have made this as 1. Okay, so here we need not do anything. Just see where 1 is pointing. 1 is pointing to 0. 1 is this 1, it is pointing to 0. 0 is visited or not? Yes, it's already visited. If it is already visited, we need not do anything. Just to go to the next node in the linked list. What is this node? 3. 3 is visited or not? No. No. So when it is not visited, you have to be careful. When it is not visited, visit it. So after 1, we visit 3. And then we make 3 as 1 in the visit array. Okay, now what should we do? We should jump to 3, because this is the first time we are visiting 3. Whenever you are visiting the node or a vertex for the first time, other than the vertex 0, you should visit it and you should jump to that particular vertex in the adjacency list. So we should jump to now vertex 3. But before jumping, you should push this particular vertex. From which vertex you are jumping? Currently you are in which vertex? 1. So this entry is corresponding to 1. In 1 only, all these, these nodes are there. These linked list nodes are there. So push 1 into stack. So now push 1 into stack and then jump to vertex 3. Okay. So 3, yes, obviously we visited 3. Now 3 is pointing to 1. Is 1 is already visited? Yes, it's visited. If it is visited, just to go to the next point, next node. So 1 is pointing to 7. Is 7 is visited? No, 7 is not visited. So visit 7. So visit 7 and make its visit array value corresponding to that as 1. Now what should we do? Now we should jump to 7. Now we should jump to the adjacency list position 7. But before jumping, you should push what? 3 to the stack, because we are jumping from where? 3. So push 3 to the stack and then jump. So now the control goes to 7. Okay? 7 is visited. 7 is pointing to where? 3. Is 3 is visited? Check the visit array. Yes, it is visited. So go to next. Next is 4. Is 4 is visited? Check here. 4 is not visited. 4 is not visited means visit it. So after 7, we will visit 4. Okay, visit 4 and make this as 1. And make this array of visit array as 1. Okay. And now where should we jump? We should jump to 4. But before jumping to 4, what should be pushed into stack? We are currently in which vertex? 7. So 7 should be pushed into stack. Push 7 into stack and jump to 4. Okay. Push 7 into stack and jump to 4. So now we are in 4. Okay. Right. 4 is visited already. Whatever you are jumping, surely it will be visited. So you need not even check that. 4 is pointing to where 1. 1 is visited or not? So how do you know? Check the array. Yes, 1 is visited. Next 1 is pointing to where 7. 7 is visited or not? Yes, visited. Then go to next. Go to the next of 7. But what is next of 7? Null. Okay, this is the third case. This is the third case. You see, three cases we are discussing. This is the third case. So if there is a null, whenever you are passing through a particular adjacency list entry, node by node, if you encounter a null, whenever you encounter a null, you have to pop. Whenever you encounter a null, what you have to do? You have to pop. So now we encountered a null. After 7, there is nothing. So we are in currently which vertex? Fourth vertex. You are going moving one by one. After reaching 7th node, there is nothing. So you pop. So pop means 7 will come out. 7 will come out, which means now our control is transferred from 4 to 7. Okay, now once again we are in 7. Once again we are in 7. Okay, right? Now you see 7 again continue. 3 is from 7. 3 is visited or not? Yes, visited. 4 is visited or not? Yes, visited. Okay. Next, if it is visited, just go next. 5 is visited or not? No, not visited. So visit 5. Visit 5 and make the entry, I mean visit entry corresponding to 5 as 1. Okay. Now we should jump to which vertex? 5. Before jumping to 5, what you should push into stack? 7 you have to push into stack. Because you are jumping from where? 7. So again push 7 into stack, but this time we are jumping to 5. This time we are jumping to 5. Okay. Now see, 5 is pointing to 2. 2 is visited or not? No, not visited. So visit 2. So visit 2. Okay. And make this visit value corresponding to 2 as 1. Now we are going to jump from 5 to 2. So before jump, so we should jump to 2. Currently we are in 5. So before jumping, we should push the current adjacency list entry into stack. What is that? 5. So push 5 into stack. Okay, after pushing 5 into stack, jump to 2. Now we jumped to 2. From 2 you see what is there? 0. Is it visited? Yes, visited. Then go next. If it is visited, just go next. Then 5. Is it visited? Yes, visited. Next, go next. Go to next. What is that? 6. Is it visited? No, it's not visited. So visit it. So what will happen? 6. So display 6 and make this as 1. Visit it. Okay. So this is the first time we are visiting 6. This is the first time we are visiting 6. So whenever you visit something for the first time, what should you do? Jump. So we should jump to 6. From where we are jumping? From 2 we are jumping. So push 2 to stack. Push 2 to stack and jump to 6. Okay. Now from 6, 2. Is it visited? Yes, visited. Then 2 to, then go next. 7. 7 is visited? Yes, visited. Then go next. Null. So whenever you see null, what you should do? Pop. So pop means 2 will come out. It means now the control again went back to 2. Now we are in 2. Okay, now we are in 2. So 2 you see. From 2, 0 is visited. Yes. 5 is visited. Yes. 0 is visited. Go next. 5 is visited. Yes. Go next. 6 is visited. Yes. Now all are visited. Then go next. Null. Null means what you should do? Pop. So pop means 5 will come out. It means currently our control is in 5. Again check in 5. 5, what is there? 2. 2 is visited, yes. Then go next. 7. 7 is visited, yes. Then go next. Null. So whenever null, pop. So when you pop, what will come out? 7 will come out. So 7 will come out. It means currently our control is in 7. Currently we are in 7. So again from 7 is pointing to 3. 3 is visited, yes. 4 is, go next. 4 is visited, yes. Go next. 5 is visited, yes. Go next. 6 is visited, yes. Go next. Null. Again null means what? Pop. So now when you pop, 3 will come out. So go to 3 now. So from 3 there is 1. Is 1 is visited? Yes. Go next. 7. Is 7 is visited? Yes. Go next. Null. So what should you do when there is null? Pop. So when you pop, 1 will come out. Okay, so it means now the control is in 1. Okay, so 1 is pointing to 0, 0 is visited, yes. Next 3 is visited, yes. Then go next. 4 is visited, yes. Then go next. Null, null, whenever you null you have to pop, so pop. Now when you pop, 0 will come out. Okay, so from 0 is 1 is visited, yes. Go next. Is 2 is visited, yes. Then go next. Null. So when there is null you have to pop. Now when you pop, what will come out? Stack is empty. When stack is empty, if you pop, null will come out. Null. When stack is empty, when you pop, the stack will return null. When it returns null, you stop the algorithm. Okay, right? This is the logic. This is the logic. Actually, already we displayed, but this is the right way to stop. Okay, it will pop, 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 and then you have to stop. When finally when the stack does not give anything, you have to stop. So you can see 0, 1, 3, 7, 4, 5, 2, 6. 0, 1, 3, 7, 4, 5, 2, 6. Okay, so this is the order of traversing in DFS. Okay, so here when you see the algorithm, there are three cases we have to write. The first is we have to write the code to implement the graph in what you call this adjacency list format. Okay, once that is done, okay, we have to start with the zeroth entry of the adjacency list. Okay, right? First display 0, then see where 0 is pointing. Surely that node might not be visited. So display that. First display 0 and make it visit as 1. Then see where 0 is pointing, then display that and also make it visit as 1. Okay, other than 0, whenever you visit a node for the first time, you have to visit it and you have to make its visit value as 0, then we have to jump. Okay, so first is what, whenever you visit a node vertex for the first time other than the root node, then the current vertex should be pushed into the stack and you should push jump to the new vertex. That is the first point. Okay, that is the first case. Second case is, if you are visiting a vertex which is already, if you are visiting a node which is already visited, I am calling this as node, the linked list things as node and this as vertex. If you are visiting a node which is already visited, then just go to the next pointer where the linked list is pointing. Just go to the next. This is second case. Okay. Third case is, if you are reaching at a null entry, you have to pop. If you are reaching at a null entry, you have to pop. These are the three cases. Okay. If you are visiting a node for the first time, then push the current vertex into stack and move on to that particular vertex which you are visited for the first time. Obviously, after visiting it and after making it one in the visit array. Okay. If you are visiting a node which you already visited, then just uh, just go to the node which is pointed by the next pointer of that particular node. Okay. If you are reaching a null pointer, then you have to pop. Okay, this is the algorithm, right? Fine. Now let us see how we are going to implement it. Let us see its coding. Okay, let us see the coding. Right. So here is the code which I have written for DFS depth first search. You can, so as usual, it is stdio.h, stdlib.h. The node definition is same, struct node, int key, struct node, star next. Okay, because we are going to maintain a linked list kind of structure, right? Then what is an adjacency list? Adjacency list is an array of pointer. Array of pointer to what? Array of pointer to these nodes. Okay, you can see this adjacency list. How it is? It is an array of pointers, but each of these pointers should be capable of pointing to a node, and a node contains what? A key and a next pointer. Okay, right? So this is our node definition. So here you see node. Node contains what? Key and next. So that node is defined like this. Okay, an adjacency list is an array of pointers. It's an array of pointers. I have given here 100. Later we will take input from the user. Okay, next stack. We need a stack also. Stack also should contain what? Stack also should contain these vertices. These vertices, actually all these are what? These are nodes. So how we are going to identify it? Using some pointers only we are going to identify it. So we are creating a array of pointers for stack also, right? and this is to hold the maximum size of the stack, and initially TOS will be minus 1. Okay, V represents the number of vertices in the graph, and there will be an array visit of 100, that will be just an integer array. Okay, initially this visit of depending on how many vertices it is there in the graph, all the entries will be filled with zeros, right? Whenever you visit a particular node, we will make it 1, right? And this is the logic to push a particular node into the, or a particular vertex into the stack, and this is the logic to pop a particular vertex from the stack. Okay, if stack is empty, if you are, when you are trying to pop, if the stack is empty, then we say that stack is empty and we return null, because in the explanation you might have observed, when the stack is null, when the stack returns null, at that time only the algorithm will stop. Okay, if stack is not null, then it will return whatever the current top of stack, then top of stack will be decremented. Okay, fine. So in the main function, if you see, first what we are doing, okay, this is the main function. First we are calling a function called create graph, which is used to create the, first we are calling a function called create graph, which is used to create the adjacency list representation of the graph. Okay, then display graph, which is used to display the graph. Okay, then we are calling this DFS. Okay, depth first search algorithm, whatever we have discussed, let us see how we are going to implement it. So first let us discuss this particular part, create graph. Okay, so in create graph, what should we do? We should create graph in the sense, we are going to create adjacency list of the graph. Okay, so how do we create that? So if you recall, first we should ask the user, like, first we should ask the user like how many nodes are there. Okay, the number of nodes will be stored in V. So here the number of or the number of vertices will be stored in V. Here the number of vertices is 8. Okay, so once you say it is 8, then we will set this visit array, visit of 0 to 7 as 0. Okay, and we will, in the what you call, we have created an array of pointers for this array list, that also we will limit to 8, 0 to 7, right? And then we will ask the user like what are the pointers for the vertex. Vertex 0 is pointing to which vertices, like that we will ask. Vertex 0 has edges to which vertices. How many vertices we will ask first. Vertex 0 has edges to how many vertices? 2. What are they? What are they? 1 and vertex 1 and vertex 2. So this, like this we will take input. Vertex 0 has edges to how many vertex? 2 vertex, and what are they? 1 and 2. Again, vertex 1 has edges to how many vertices? 3 vertices. This also you should consider. 1, 2 and 3. 3, it has edges to 3 edges. How many edges it has? 3 edges. And to what are the nodes or what are the vertices connected to that? 0, 3 and 4. Okay, 0, 3 and 4. Okay, this order of entry is important. Okay, see, in adjacency list when we are discussing, we discussed that this order is not required. This order can be of any way. It can be, instead of 0, 3, 4, it can be 4, 3, 4, like that we have discussed. 4, 3, 0, like that. But that is for adjacency list. But for depth first search, order is important. Please remember. Okay, for example, vertex 0 has connection to two nodes 1 and 2, means you should enter as 1, 2. That means first we have to enter the left child, and then the next left child, then the next child, and then the rightmost child. This order should be important. Otherwise, traversal will not work correctly. Are you getting? Okay, fine, right? So similarly, if vertex 1, if you see, it has pointer to its parent v0 and then to its child. So whenever there is a parent pointer is there, first you have to mention the parent pointer. Okay, if there are more than one parent pointer also, first you have to mention that, also you have to mention from left to right. Okay, so here you have to mention first vertex 1 has how many edges? 3 edges. And what are they? 0, 3, 4. First you mention the parent edges. Then vertex 2 has how many edges? 3. What are they? 0, 5 and 6. Okay, vertex 3 has how many edges? 2. What are they? 1 and 7. 4 has how many edges? 2. What are they? 1 and 7. 5 has how many edges? 2. What are they? 2 and 7. 6 has how many edges? 2. What are they? 2 and 7. Okay. 7 has how many edges? 4. 7 is pointing to how many nodes? 4. What are they? 3, 4, 5, 6. Okay, like this we will give entry. Then this adjacency list will be displayed. Okay, fine. Let us see that code now. So that is what in create graph is there. So here we are creating some variables, and there is a new node we are creating, struct node store new vertex. Okay, this is just a pointer, it's currently not holding anything. And then traverse, we are also creating a pointer traverse. Then we are asking the user to enter the number of vertices in the graph, that we are loading in V, scanning in V, and max size is set as V. Then for I is equal to 0, I less than V, I plus plus. For every node we are going to ask the user, enter the number of nodes to which edge exists from vertex percentage %d. So initially percentage %d is means I. Initially I will be 0. So how many nodes, enter the number of nodes to which an edge exists from vertex 0. From 0, how many nodes are connected to an edge, that we are reading. From 0, 2 nodes. Okay. Then we are asking the user to enter the vertices to which edge exists from vertex 0, from leftmost to rightmost. Okay. So first we are asking the number of edges, then we are asking to enter what are those vertex to which this 0 vertex connects. Okay. So right. So that, so number of vertex to which 0 connects, number of edges it has already we have read in n. Okay. So for j is equal to 0, j less than n, j plus plus, we are reading one by one vertex to which there is a direct connection exists from the root node, that is 0. We are reading it in VER vertex. Okay. Then we are creating a pointer for the new vertex. We are allocating the memory for the new vertex, which here at the top which is declared. Okay. New vertex equal to struct node star malloc size of struct node. Okay. And a new vertex arrow key is equal to vertex, whatever the value we have given. And its null will be, and its next will be null. Whenever we add a what you call a vertex, initially we will set its next as null. Okay. Right. Now, now what can happen? This new vertex may be the first vertex of that particular entry. This new vertex may be the first vertex of that particular entry in the adjacency list. See, this is adjacency list 0. This is adjacency list of 1. This is adjacency list of 2, so on and so forth. Now, when you add a node, we don't know whether it is the first node or any other node. Okay. How do we identify whether it is a first node or not? For that, we are checking here. We can identify whether it is a first node or not by checking whether j is equal to 0 or not. Okay, if j is 0, then that is a first node. Okay, right? Because all, see, this is represented as I. This 0 to 7 is represented as I. This child of 0 is, I mean 0 has a direct pointer to 1 and 2. This is represented as j. Okay. So this will be J0, J1. This will be 0, 1, 2. This will be 0, 1, 2. Okay. So if J is 0, then it is the first child of this particular entry in the adjacency list. Okay. Right. So if J is 0, then we are directly adjacency list of that entry will point to that. So adjacency list of I is equal to new vertex. Okay. Right. And adjacency list of adjacency list of I arrow next is equal to null. That you may not also specify, already it is given here. Already it is given here, this is not required. Okay. Else, if that is not the case, then we don't know already how many nodes were added. Okay, already how many nodes added we don't know. So traverse equal to adjacency list of I. Okay, say for example in this you are trying to add this particular node 4, but already 2 nodes are there. So traverse is equal to adjacency list of I. Adjacency list of I is this. This is pointing to where? 0. So you are creating a pointer to here. I mean you are creating a pointer that will point to where adjacency list of 1 is pointing. Adjacency list of 1 is pointing to this node. Okay, so traverse also will point to this node. Traverse also will point to this node. Okay, then what we do? traverse equal to adjacency list of I, while traverse arrow next not equal to null, traverse equal to traverse arrow next. So then we check, is traverse arrow next is not equal to null, yes not equal to null, then go to the next node. Then check its next is not equal to null. Here if 4 is not yet added, then its next is null. So come out. So come out when traverse is pointing to 3. When traverse is pointing to node 3. Okay, then after coming out we will say traverse arrow next equal to the new vertex. So 3 arrow next will be the new vertex, that is 4. Okay. So this is how we add the vertex into the respective entry in the adjacency list. So like this for every, I mean every, so this outer loop, if you see, it is going to repeat for all the vertex. Okay, this is going to repeat for all the 8 vertex 0 to 7. This inner loop is for each vertex, how many edges are existing for some other nodes. Are you getting? Like that we are adding. Okay, this display graph, it will just display the adjacency list. Okay, in the adjacency list style. Instead of display graph, you can call it as a display adjacency graph, adjacency list also. That will be more appropriate. I just named as display graph. So it will just display this adjacency list. Uh, like 0 is pointing to where 1 is pointing to 2, again 1 is pointing to 0. This adjacency list it will just display. Okay, it will just display so that we can ensure that adjacency list is created properly. So here also we are creating traverse. Then for I is equal to 0, I less than v, I plus plus, v is the number of vertex. Traverse equal to adjacency list of I. So now traverse is pointing where adjacency list of 0 is pointing. Adjacency list of 0 is pointing to where first node it is pointing. Okay, right. But first what we are printing is I we are printing, because 0th node also you should display, right? So so I we are displaying, because currently when I is 0 it means we are in 0th vertex, and 0th vertex is pointing to some other vertex. Okay, so this will display 0. Then while traverse not equal to null, print of percentage d traverse arrow key. So after 0 it will display what? 1. Okay, then traverse equal to traverse arrow next. So that is 2. Okay, then traverse is not null, it will display 2. Then again traverse arrow next means it becomes null. So if it becomes null, we display null. It will come out of the loop, then we display null. So after the one iteration of the outer loop, it will display like this: 0, 1, 0 to 1, 1 to 2, 2 to null. Okay, but actually our understand, this is just a display of the adjacency list. But we know our understanding is there is a pointer from 0 to 1 and a pointer from 0 to 2. But there is an edge from 0 to 1 and an edge from 0 to 2. Okay, right. So this is one entry. Okay, then again I will become 1. When I becomes 1, traverse is equal to adjacency list of 1. Adjacency list of 1 means this. Now traverse is pointing here. Okay. Now again we will display I. I is what? 1. So next line will display slash n. So now 1 will be displayed. While traverse arrow null not equal, while traverse not equal to null, again the same story. So now it will display what in the next line? 1. Then traverse arrow key. See, initially traverse is traverse equal to adjacency list of I means it doesn't mean that traverse is pointing to 1. No. Traverse is pointing where 1 is pointing. 1 is pointing to where? Adjacency list of 1 is pointing to where? 0. Okay. So when you say traverse arrow key, it will display 0. So that this 1 we are displaying outside the loop. You getting? So again it will point to next. Is it null? No, not null. So after 0, this 3 will come. Again next. Is it null? No, not null. So it will display 4. Again next. Is it null? Yes, null. So it will display null. And then it will come out. Then it will come out. And then go to the next. So on and so forth. Right? Like that, basically it will display the adjacency list. Okay? Fine. Now let us see the code of DFS. So before that is initialize visit. So this initialize visit function, what it does in the sense, it just makes all the, visit is an array. Okay, in this visit array for all the particular vertex, it will make the entry as 0, which means none of the node is visited yet. So if here you are declaring a variable I, then for I is equal to 0, I less than vi plus plus, visit of I is equal to 0, which means this node has not been yet visited. Okay, fine. So this is the code for DFS. Here we are declaring a local variable I and we are creating a traverse pointer. Then we are calling first initialize visit. Because first we are making sure that none of the nodes are visited. So all the nodes the visit will be set as 0. Then we are displaying DFS traversal. First we are see first node is root node. Okay. We are assuming that all the root nodes are numbered from 0. Okay. Okay, now we are not using any alphabets or anything. So first anyway we have to visit root node. So we are displaying printf backslash n 0, which is to visit the root node. Okay. After visiting root node, we are making visit of 0 equal to 1 because we have visited the root node. So make visit of 0 equal to 1. Right? Getting? Then what we do, traverse is equal to adjacency list of 0. What is adjacency list of 0? Adjacency list of 0 contains some value. What value it contains? Actually, it is an address. It is pointing to 1, node 1. See, if node 1's address is if node 1's address is 2000, then adjacency list of 0 will contain 2000. Say I am talking about node 1's starting address. If its starting address is 2000, then adjacency list of 0 in this location what will be there? 2000 will be there. Okay. Are you getting? When you say traverse equal to adjacency list of 0, so here what we are saying, traverse equal to adjacency list of 0, then traverse also contains 2000. Then traverse also contains what? 2000, which means it means traverse equal to 2000, which means what? Which means traverse is pointing to the location 2000. It means traverse is pointing to this particular node. That is the meaning. Okay, here if it contains 2000, what is the meaning? It is pointing to this node, so that the pointer comes. Are you getting? Okay, right? Fine. So now we are making traverse to point to where adjacency list of 0 points, because adjacency list is nothing but an array. Okay, now here we are writing an infinite loop while 1. Okay, when this loop control will come out means when the stack becomes empty, when the stack returns null. Okay, so now we are checking if traverse is not equal to null. Currently traverse is not equal to null and visit of traverse of key is equal to 0. Okay, yes. So traverse is pointing to this node. What is its key value? 1. Is 1 is visited now? We have visited only 0. Is 1 is visited? No, it's not visited. So it is 0. So is this condition is satisfying? Yes. Traverse is not null and visit of traverse arrow key also is equal to 0. Then what should you do? Visit that. Okay. So visit means what? Display that. So when you display that, what will display? So already we have displayed 0. So now 1 will display. And then we are making visit of traverse of key is equal to 1. So so now we have visited 0 and then 1 and its corresponding visit value will be here made as 1. Okay, right. Then what we are doing, push of traverse. What is traverse? Push of traverse means what? See, traverse contains what? Traverse contains whatever adjacency list contains. Okay, so uh, I mean traverse contains whatever adjacency list of 0 contains. Okay, so we will simply mention as 0, which means vertex 0. So vertex 0 is pushed into stack. Okay, otherwise I have to give, actually 2000 will be pushed, right? Then I have to give address for everything, or you have to assume that this is pointing to 2000, this is to 3000, 4000, 5000, 6000, 7000, something like that. Okay, then you can say it is 2000, right? I am simply saying 0 is pushed. 0 is pushed into stack. Now what we are doing, now traverse equal to adjacency list of traverse arrow key. What is traverse? Traverse is pointing to this node only, even though you have pushed. Okay, but still traverse we have not made anything as null or anything. So traverse is pointing to this particular node. Now what we are saying is traverse is equal to adjacency list of traverse arrow key. What is traverse arrow key? 1. Okay, 1. We are saying traverse equal to adjacency list of traverse arrow key. What is traverse arrow key? 1. Adjacency list of 1. Then now we are saying traverse equal to adjacency list of 1. What is adjacency list of 1? Adjacency list of 1 is this. Maybe it may contain some other address 3000, which means that the starting address of node 0 is 3000, which means that starting address of node 0 is 3000. Okay. So now traverse is pointing to where? Here. This zeroth node is pointing. You getting? Right? Fine. After that, there is else if. In our case, we are not executing else if. So else if will execute if traverse is equal to null. If traverse not equal to null and key is equal to 0, then this will execute. If traverse equal to null, then what you should do? Pop. Traverse equal to pop, and then you have to check after popping. You have to check if traverse equal to null. Okay, because when the stack will return null, if the stack is empty, if it is null, you break. If these two conditions were not satisfied, then it means that traverse is not null, but that particular node is already visited. Then just we move on to the next node. Traverse equal to traverse arrow next. Okay, but in our case we are jumping to a new node which is node 0. Okay, again all this process will repeat. Again for the node 0 we will check. What we will check? Well, first we are pointing to node 0. So traverse is not null, but is this node is visited? Yes, 0 is already visited. If you see here, 0 is already visited. So what will happen? Else if will not execute, else will execute. Traverse equal to traverse arrow next. So which means now it points to 3. Okay, after pointing to 3 again it will come back and check. Is traverse not null? Is this visited? 3 is not visited because it is 0, still 0. So visit that. Visit means display that, make it 1, push the current traverse to stack. Current traverse is nothing but 1. Push 1 to stack and jump to 3, so on and so forth. Whatever we have discussed in the previously, the same thing will happen. You can work out on this, build on this stack. Are you getting? So this is what that particular function does. Okay, fine. Now let me execute this code and I will show you. So let me here. I'm compiling. Enter the number of vertices. So this is our graph, right? Number of vertices are 0 to 7, that is 8. So 8. Enter the number of nodes to which edge exists from vertex 0. How many nodes and edge exist from vertex 0? 2 nodes. So 2. Okay. Enter those nodes. What are those nodes to which an edge exists from vertex 0? What are the nodes? 1 and 2. Okay, so 1 and 2. Then enter the number of nodes to which an edge exists from vertex 1. How many nodes? 3. 1, 3. Okay, 3. What are they? What are they? If you see here, 0, 3, and 4. So 0, 3, and 4. Then enter the number of nodes to which an edge exists from vertex 2. Vertex 2 again 3. 1, 2, 3. So 3. What are they? What are the nodes to which an edge exists from 2? 0, 5, and 6. So 0, 5, and 6. Okay. Then enter the number of nodes to which an edge exists from vertex 3. 2, 1, and 2. Okay. 2, 2. Okay. What are they? What are they? Vertex 1 and vertex 7. So it is 1 and 7. Again enter the number of nodes to which an edge exists from vertex 4. Vertex 4 to which nodes edge exists to which vertex? 1 and 2. 2 vertex. Okay. So 2, and what are they? Again it is vertex 1 and vertex 7. So 1 and 7. Enter the number of nodes to which an edge exists from vertex 5. Vertex 5 again 2. This one and this one. Right? 2. And what are the nodes or vertex to which it connects? To 2 and 7. One is 2, other one is 7. So 2 and 7. Okay. Similarly, vertex 6, how many edges are going? Only 2. Okay. So what are the nodes to which it connects? 2, again 2 and 7. So 2 and 7. Then vertex 7, enter the number of nodes to which an edge exists from vertex 7. 1, 2, 3, 4. Okay, 4. 4. What are the nodes to which it connects? 3, 4, 5, and 6. So 3, 4, 5, and 6. Okay, you can see this is the what you call adjacency list. You can check out 0, 1, 2. Okay, 0 1 2 1 0 3 4 null. Okay, 2 0 5 6 null, 3 1 7 null, 4 1 7 null, 5 2 7 null, so on and so forth. Last is 7 3 4 5 6 null. Okay, and this is the DFS traversal 0 1 3 7 4 5 2 6. 0 1 3 7 4 5 2 6, right? Okay, so that's it about this algorithm. So here I have two versions of code for DFS. One is without recursion, another one is using with recursion. Okay, this is the code which we have discussed is without recursion, where we ourselves pushed into by ourselves. Okay, but actually you can write a recursion version also, which will be very simple, where the stack involvement is not required. But for your understanding, I have shown this non-recursive version also. Okay, actually in your textbook the recursive version is only given. This non-recursive part is not given, but the explanation in the textbook, it clearly explains what is happening in the stack, all those things. Okay, so I wanted you to understand, so that I wrote this code. Okay, so you should also write this code, so that you know really what is happening. Okay, whereas in the recursive code, whatever we have discussed in the non-recursive code, all these things will happen, but all these things will happen automatically. So this is the recursive code. You see here we are. I'll show you how I'm calling it from the what you call main function. So in main function DFS, this is not recursive DFS, which we are calling directly. When you call recursive DFS, what I am doing is printf recursive DFS. Then here itself you are calling initialize visit, not there, because you have to call that recursively. Okay, when you call recursively inside, you cannot write initialize visit. Then every time it will become zero. I mean, every time all the nodes will become unvisited. Okay, so here we are calling initialize visit. So initially it will set that all the nodes as not visited. Okay, and we are recursive df, we are calling recursive DFS, and we are sending a pointer. What is that pointer? Adjacency list of 0. Adjacency list of 0 is a pointer, right? This pointer we are sending, it is pointing to which node? Node 1. That pointer we are sending. Okay, so it takes one argument, that is a pointer, right? Fine. Then what it does, let us see. So it contains a pointer which is same as that of the adjacency list of 0. So in our example, adjacency list of 0 is pointing to what you call, it is pointing to this particular node 1 in the adjacency list. Okay, then we check. First, after coming here, we are declaring some node w. We are checking whether 0 is visited or not, because first you have to visit 0, right? So initially only for the first time when it comes in, 0 will not be visited. So if 0 is not visited in the in the visit list, then first we are visiting 0 and we are making visit of 0 equal to 1. So this will execute only for one time. Even the code can be recursively called any number of times, but it will execute only for the first time when it enters. Because anyway we have to first visit 0, so we are making sure it happens here. Then we are assigning this w equal to v. What is w? This is the node we are using. Okay, and v is what? What you passed. What is adjacency list of 0? So w is equal to v, while w not equal to null. While w not equal to null, w equal to w arrow next. So initially w is pointing to node 1. Okay, then we check whether w arrow key is equal to 0. That is 1. Node 1 key is 0 or not. W arrow uh, not key, visit. See, this is, sorry, this visit. So visit of w arrow key, that is in the visit array, w arrow key is 1. The visit of 1 is no, 0 or not. Yes, it will be 0. So you, what you should do, then visit it. So we are making it 1 and we are displaying it. After displaying, what should we do? We should jump to that node. Which node? Vertex 1. Currently we are in vertex 0. Initially from main function we called this with what? Adjacency list of 0, but now you have to jump to adjacency list of 1. So again we are calling recursive DFS as adjacency list of w arrow key. What is w? W is pointing to that first node. So first node's key is 1. That with that node, so adjacency, so this will become 1. So w arrow key is at this point it is 1. So it means adjacency list of 1. Are you getting? First time when we called as adjacency list of 0. Now it will be recursively called as adjacency list of 1. Okay, right? But as it is a recursive function, whenever a function call happens, what will happen? Current temporary variables will be pushed into stack. So when you call as adjacency list of w arrow key, obviously adjacency list of this is called as adjacency list of 0, that will be pushed into stack. So 0 will be pushed into stack and then control will go here. So here pushing happens automatically, right? And similarly whenever a null comes, so otherwise if there is no issues, this will be keep incrementing. I mean, if it is already visited, it will be keep incrementing. But at any point if it becomes null, then automatically that pop will happen. So you need not write that. All this implicitly happens. But in the other code, we are writing it explicitly, right? So both the outputs are same. You could have checked here. Okay, here you can see this is the output from the DFS traversal. This I mean non-recursive DFS traversal. This is the output from the recursive DFS traversal, right? So that's it about DFS traversal depth first search. Okay. So if you implement depth first search using adjacency list, the complexity is order of E. That is, how many edges are there, that much I mean that much search or that much things we have to access. Okay, because you see here there is no waste edges are there. I mean for every vertex, only if there is edge we go. Otherwise there is no edge means we don't go. Are you getting? So the number of operations you want to perform is order of E, which is equal to the number of edges in the graph. Okay. But if you implement it using what you call if you implement it using adjacency matrix, if you implement it using adjacency matrix, then the number of operations will be order of n square. Okay, because you remember in adjacency matrix, we maintain all the entries. 0 means there is no edge, 1 means there is edge, 0 means there is no edge, 1 like that. So here, there, even if it is a 0, you have to go and check whether 0 is there or not. If 1 is there, we will consider, but 0 we will ignore. But still, you have to check all the entries. You have to check. So how many operations you want to perform? Whether it is 0 or not, that also you have to check. That is also an operation. So how many operations you have to perform with the adjacency matrix is order of n square. Okay. Whereas with the adjacency list, it is only order of e. Okay. So so n square means for all the nodes n into n square thing you have to check. Okay, right. So so the point is depth first search can also be implemented using adjacency matrix. The way of working is similar only. You can try implementing depth first search using adjacency matrix. You can take that as a homework, right? Fine. Otherwise, we'll stop here. Thank you.